Okay, let's wait for our interpreters to warm up, huh? Okay, now we're compiling. Whoa, hey, I almost didn't notice you here. The biggest JavaScript conference in the world ever to date. Holy smokes, that's incredible. Thank you. So, yeah, go ahead. So I'm Nick. That's me there in the red. And today we're going to be talking a little bit about WebVR. So hopefully our booth wasn't too crowded. Obviously, they're way too noisy. Who here made it to our booth, and who was the first time they ever experienced VR headset today at Mozilla's booth? Wow, okay. So who has never tried VR before? No one has put the headset on. Okay, there's a great deal, many people. So today, everyone who just raised their hand, I made a demo just for you. This is a toy. I built it really quickly. It's very simple. You know, our world was built in 11 days. This was a little bit rougher than that, but so I have this demo. If you search for it on GitHub, I understand this Wi-Fi is a little spotty right now, but if you look for something called Josh VR on GitHub, let's blow this up a little bit and resize everything. So this is a really simple demo that will allow you to build something with WebVR, and I'm going to invite you while I'm talking. If you have an internet connection, feel free to find this and hack on this and build something while I'm talking. Right? This talk's being recorded. You can actually see it later, kind of thing. But if you build something and then take this to our booth, you'll be able to plug in the headset and actually experience the scene that you built. So you can see it's really basic here. We just have groups of primitives, and we can describe transforms on them. So if I want to add something, we'll add a cube, and maybe I'll add a translate X component. And so we can see here, and it's XML, so we need to have that closing tick. And if we go to our controls here, we can see we get dynamic controls for these items. And so if we want to add a bunch of things together, maybe we'll give it a rotate Y, and we'll get some new controls for that scene. And now we can rotate it about its own Y-axis. And let's say we want to compound or group these series of transforms. We can place any of these primitives in their own tag or their own group. And we'll give the group a rotate Y. And if we do that now on our group, we can rotate the item about the Y-axis as opposed to rotating it about its own Y-axis. So now once you're able to build a really simple scene with this, if you click and enter full screen, you'll see this will actually set up this stereoscopic rendering, which is what we need to do for WebVR. And so kind of without anything plugged in, it's not quite as exciting. But if we take a look at a pre-recorded video of what it looks like. So if you plug this into a headset, you can now jump into full screen and experience the scene that you just built. So I'm going to encourage everyone, maybe there's no Wi-Fi right now, but maybe tonight, work on something and bring it back to our booth tomorrow. And we'll get that hooked up in the booth and running for you tomorrow. And we actually have a bunch of t-shirts to give away to some of the best scenes that people build. So it's obviously very limited, very constrained, but I'm confident that people can build some probably pretty neat things with it. So again, that's called Josh VR. Go ahead and tweet at me if you have a scene that you built. In fact, I made it really easy to share items. So I'm not sure that I have Wi-Fi, but if you were to click the share button at the bottom, of course, you'll get a little URL will appear, and it's actually going to publish this as an anonymous gist to GitHub. And so what you can do now is if you grab the raw URL to this gist, you can go back to the scene and click load and paste in the raw raw URL to the gist, and you can load a friend scene. So you can share with them, and even if you click search for more, you'll be able to find more. So please, if you have the time, hack on this, try and build something neat, and then come and experience what you built. Instead of seeing our pre-made demos for VR, build your own experience. And so a little bit, kind of setting the stage for what I want to talk about today, is basically the performance constraints that are imposed by VR. and kind of some of the things that we need to add to a browser to match feature parity with native in order to hit these higher performance constraints. So as a quick refresher, if you're trying to hit 60 frames a second, right, that's the monitor's refresh rate. You don't need to be updating your scene maybe more than 60 times a second. Maybe your physics calculations, maybe you do. So the inverse of the hertz is in milliseconds is how much time do you have to draw each and every element that appears in the scene. So for a 60 hertz monitor, you get 16.6 milliseconds to draw everything. Now, for VR, there's been a lot of research into like motion sickness, and researchers have found that you get roughly 11 milliseconds to render a scene before people start to feel a little sick, right? The more latency that there is between their actions and our real-time rendering, the brain starts to feel a little confused. But the thing is not only do we only have 2/3 the time to draw the scene once, we have to draw everything twice because we're rendering, it's called stereoscopic. So you're seeing the scene from two different viewpoints. So as long as it takes to draw your whole scene, now you get to draw it again in 2/3 the time. And it's not as simple as simply drawing it once and drawing it a second time because your eyes are actually offset a little bit. And for things that are close, they're maybe a little inverted versus things that are far away, they're more parallel. So there is extra work you have to do to switch between those two viewports. It's not as simple as saying draw one, draw two. It's draw one, switch a bunch of things out, draw a second time, all of that in 2/3 the time. And another interesting thing that we're hacking on is something called CSS VR. Is basically, it's not quite ready yet, but an interesting concept to think about is being able to preserve depth information between kind of like the z-index in CSS and the depth buffer in WebGL, and actually be able to position any HTML element three-dimensionally in a WebGL scene. So if you're interested in this or learning anything more, obviously come visit our booth. We also have a mailing list that's very active where you can learn all about these things. So I encourage you to join it. This link and all these slides and everything are, I tweeted them out earlier, so you'll probably be able to find them with all the hashtags and usually. So who here has heard of WebAssembly before? Has anyone seen it in practice yet? I think a lot of people are very interested in WebAssembly, but they don't quite know what it is yet, and you end up seeing a lot of different really interesting things. And when I think about the work that Mozilla is doing with Emscripten, if you've ever seen the size of some of these cross-compiled code bases, they are very, very large. And so from our perspective, our interest in WebAssembly and having this native format, or this binary exchange format, is to basically minimize load times, right? When we have these large JavaScript code bases, not only does that cost us bandwidth, but it also is a lot of work for the JavaScript engine to parse all of that code. So what's interesting is that it takes this inspiration from the LLVM toolchain as a compiler, where the intermediary representation is both a binary format and can be converted back and forth to a text format. So it can be human readable and human writable. And there's a disassembler and an assembler to go back and forth between the two. And so from day one, WebAssembly will have this. There will always be view source for this binary format. You'll always be able to convert it back to text and make it human readable. And on top of that, we can then get rid of all those type annotations that we use in WASM.js, all those kind of like bitwise or with 0 or unary plus operator. What's interesting is by using this binary format, it's basically a way of representing an abstract syntax tree. We can actually get the same program about 30% smaller when gzipped than WASM.js code in the textual representation. And then on top of that, we're not limited just by using gzip. We can use even better compression algorithms like LZHAM or a couple of the other ones and get even better, upwards of 50% compression. And not only is it smaller to ship across the wire, which is important, but it can be parsed more than 23 times faster than very large WASM.js modules. So all browsers support WASM.js, but if you feed them too much JavaScript, maybe they they weren't expecting that. This binary format can kind of be plugged right into the virtual machine without lexing and parsing, right? There's still some validation that goes on, but this can actually speed up a potentially slow phase in the pipeline. I think one of the most interesting articles I've seen, right, talks about like the death of JavaScript, WebAssembly. Is that like what Mozilla's trying to do here? And I can confidently tell you, like, no, that is not what we're doing here. This is all about limiting the bandwidth that downloading very large applications takes and improving parsing performance. So I think maybe some other folks today or tomorrow will have a little bit more information on WebAssembly and what it can be, but there's no plans from Mozilla for removing JavaScript. So now for these games, right, being able to load them up quickly is important, but to get the performance we need to talk a little bit about concurrency versus parallelism, and we saw some of these topics touched on earlier, right? So the way that I think about these two, and everyone confuses these two terms, but if a task is interruptible, that's when I think of it as being concurrent. And if you have these tasks that are independent of each other, that's when they become very easy to make parallel. And one of the things that's interesting is there are instances or cases where a task could be interruptible but not independent, or it could be independent but not interruptible, or it could be both, or it could be neither. And so when we think about JavaScript and its use of callbacks, right, the language itself isn't necessarily concurrent, right? We can't just interrupt the middle of like a while true loop, but with Node.js, for instance, we're able to do some file-based I/O or network-based I/O, and then continue processing things on the main thread, and then later on we can run tasks when our I/O finishes. And another important concept to know a little bit about is synchronization. So probably the best example of this that I can find is this is what I used to do in track back in high school. And so if we think about the runners here as threads and the batons they're handing off as the data, what's interesting is if we go back, you can see the first threads are paused. They have to start running a little bit sooner, but they can't take off fully until they have the data that they need, right? They will get disqualified. And so we can kind of think about parallelism a little bit like this, or synchronization at least, because the two runners, they have to synchronize. The handoff, it doesn't look like there's a whole lot going on there, but you can actually get disqualified for dropping a baton in the middle of the handoff, right? And I think of that as kind of like a data race a little bit. So again, it seems very simple, but there's actually a lot of hard work that goes into synchronization. So one of the new APIs that we're working on is something called SharedArrayBuffer. And what this does is this allows web workers to share an instance of a typed array. And they both have read and write access to the typed array. What's very important is that a shared array buffer is not accessible to the main thread. Now, when I say shared memory, this is the first thing that comes to my mind. So this guy is saying, you call throwing dynamite around a martial art? And this guy says, hey, as long as it works. So usually I like to think of shared array buffer as a last resort, but we're kind of at the mercy of hardware vendors, right? Like for software, we might think, the ultimate abstraction is some Lisp-like thing, whereas the hardware vendors think that a state machine is like the most elegant thing. So some of the problems that this introduces, the use of shared memory and why we've kind of been avoiding it for a long time in JavaScript, is that it can lead to data race conditions. Awful things where you have two threads reading, modifying, and then writing to the same address, or maybe the same element of a typed array, and getting different results back on subsequent reads. Or awful things like the ABA problem where one thread replaces an instance that's referred to in a first thread with something that looks exactly like the same instance, but it's not. We can also cause deadlock. So if we have any kind of mutual exclusion abstraction and we kind of halt a thread or put it to sleep in a critical section until a lock is required, if we don't carefully unlock the lock when we don't acquire it, we can lock the thread, where basically it stays asleep forever. So it's almost like a while true loop, but the thread is still running. It's just very busy doing like jumping back kind of thing. Deadlock is the thread's asleep and it won't be woken up. And other things like live lock is another kind of issue that you have to worry about as well with shared memory. So this is a photo that hangs in Mozilla's SF office. This is one of our principal engineers, one of the best engineers we have at the company. And he stands underneath the sign that says, "You must be this tall to write properly multi-threaded code." So it's a little disheartening, but there's tools that can help for that. And so the API for SharedArrayBuffer gives us a few very basic building blocks. It gives us these things called futexes. You can think of them like a mutex. They're actually this idea that's available in the Linux kernel. And it also gives us access to atomics, so atomic increment of various sizes of variables. And on top of those two basic abstractions, we can build all the other systems programming building blocks, such as locks with mutexes or simple spin locks. We can build condition variables that notify other threads that it's time to wake up and begin processing. We can build semaphores, which limit how many tasks are allowed to run or have access to a resource at a given time. And so theoretically, it's possible for someone to build a library on top of these called mutex.js. Now, you don't have to do this. If you want, you can go and see someone at Mozilla already has. So in the Emscripten code base, someone has ported libpthread over and has this available in Emscripten. So it is possible to implement this in JavaScript. Now, I would not recommend writing maybe handwritten JavaScript using SharedArrayBuffer because, like we saw with the sign earlier, it's very difficult to set up synchronization correctly. So my advice is always to prefer task-level parallelism with post message and transferring the ownership of typed arrays to data-level parallelism with SharedArrayBuffer. But with that said, sometimes having a thread-safe data structure can be really important, especially for very, very performance-critical applications like real-time rendering game engines, for instance. I think another piece of advice is that other languages have maybe better tools for probably writing multi-threaded code. C++ and Clang, the Clang toolchain has thread sanitizer, which can, at runtime, detect when you're running code that's not properly using mutual exclusion, for instance. And the prophecy tells of another language coming out soon from Mozilla that will help even further in this regard. So maybe if you've heard of Rust, but that's a story for another conference. Another API we're working on is WebGL 2. So when I think about synchronization between the CPU and the GPU, I think of like tumblers spinning, right? And I think of like the CPU has a way higher clock speed than the GPU, but the GPU's got a whole bunch of these like tumblers going. It can process tons of data at a time. It just moves a little bit slower than the CPU does. And so one of the issues with interfacing between the CPU and the GPU is you always want to minimize the amount of contact the CPU has with the GPU. You can think of it like maybe like a clutch on a motorcycle, how you have to, the faster gear has to slow down to bring the slower one up to speed kind of thing. So this is effectively the family tree for the OpenGL family. We can see WebGL 1 was based on OpenGLES 2, and WebGL 2, which will hopefully be out this year, I don't know, but the spec is being written, and our implementation is pretty close. It is based on OpenGLES 3.0. And so it adds a bunch of new things. In WebGL 1, it has this concept of extensions, which is something basically you have to feature test for. And if it exists, you can use it, and it makes things faster and nicer, and there's less synchronization. Otherwise, you have to implement it yourself. You have to fall back. And there's a few new things that are impossible to implement in WebGL 1. So things like vertex array objects simplify switching shader programs. Instancing allows you to draw multiple copies of the same geometry while using less memory. Multiple render targets simplifies things like deferred rendering and click detection. So, for instance, if we take a look at this video. This is a three-dimensional home screen that I made for Firefox OS. I guess we can make that full screen. So this home screen, it grabs all the apps, and then to detect where a click is, the technique that's used in a lot of 3D code basically is to render everything twice. So you render everything once, where each geometry is a different color. Then you have to capture the click event and translate the coordinates from DOM coordinates to canvas coordinates. You read the pixel back, you read what color it was, and if it was red, then you have to map that back to which application or which geometry you clicked on. And then when you're done with that, then you do another pass and you render everything on top of it how you actually want the user to see it. So they never see it in between. Multiple render targets will allow you to do both of those in essentially one step. Uniform buffer objects help switching between shaders as well. Memory barriers are synchronization primitives. But one thing that's going to be missing that a lot of people have been asking about is geometry shaders, which were available in OpenGL 3.1. Won't be in WebGL 2 from the get-go, maybe as an extension. The next thing that's really interesting as far as parallelism is concerned is Simdi, is single instruction, multiple data. And so the idea is, let's say you have 4 pairs of numbers that you want to multiply. So you'd say A times B is equal to whatever, C times D, E times F, G times H, right? So you have to do those multiplies in 4 instructions. That's single instruction, single data. Simdi instead is basically saying, treat these two pairs of values as an array and go through and multiply them all in a sequence. So excuse my confusing use of color here, but if we have a vector times another vector, we'll get 9 times 4 is 36, 7 times 3 is 21, 2 times 6 is 12, and 10 times 4 is 40, right? So in one step, a Simdi instruction can multiply all of these numbers together. And one of my favorite patterns that I see with Simdi is interesting, is kind of how they handle conditionals. So this is a select operation. So we can just imagine that if an element is greater than some value, assign it to one value, else the other one. And so one of the ways that we can do this with a select, basically how this will be implemented in Simdi, is you end up generating a mask you evaluate for each element, and you generate a mask. So the same length, but you can think of those as like Booleans, so false, false, true, false. And then you bitwise and the mask with the values, so you wind up with 2 of these arrays, and then you pass select the true mask and what would have happened in the true branch, else the false branch, and that's how you wind up with the result. So what's interesting here is rather than branching or jumping forward, instead we evaluate both code paths, then evaluate the conditional, then mask off the results based on the conditional. And this is actually how fragment shaders work on your mobile device. So that's why if you've ever tried to do anything really crazy with Shader Toy and have like a Mandelbrot set or something interesting like that, your phone will probably catch on fire and explode, because for every additional nested branch, you'll see this kind of grows exponentially in how many paths it has to evaluate. One of the things I'm proud to announce is recently we landed patches in GLMatrix, is one of my favorite linear algebra libraries, for Simdi optimizations, and we figured out a way to implement it in a way that respects forwards compatibility. So if you're using GLMatrix today, you can simply upgrade what version of GLMatrix you have, and in Firefox Nightly and in Microsoft Edge, you'll see significant performance boosts. So I don't have any numbers yet. When we do, we'll do a Hacks blog post, but keep your eye out on that. And I think one of the reasons why Simdi is important is that all of this is being done on the CPU, and we're not handing data off to the GPU, right? So the GPU can crunch way more numbers, but it takes a little bit longer to spin up the context and pass the data over to it, and have it crunch the numbers, and then read the data back. So you have to profile and figure out where this performance pays off on the performance curve. But with Simdi, we don't have to transfer these elements off of the CPU. Everything stays on the CPU. It's a lot simpler to write code that uses Simdi, and get performance wins out of Parallel for free. And the final topic I want to talk about is WebGL workers, where basically what we're going to do is allow all of the WebGL calls to be made from a worker thread. So right now it doesn't look like there will be request animation frame. So instead in your main loop you have request animation frame, and it has to post message with a time to a worker. And then in the worker, it can keep track of the time differential for velocity-based animations and stuff. But what's interesting is that for the first time, you'll actually be able to modify what the user sees on the main page, but not from the main thread, kind of thing, which will be interesting. And so my prediction is, I think going forward, a lot of people, they're confused about the DOM, about performance. I mean, the grass is really not greener on the other side of the fence in WebGL. Like that picking code, I can't tell you how I just wish I could assign an on-click handler. It would make things so much simpler. But I think we'll begin to see more and more things be moved off the main thread as far as APIs are concerned, especially if we can render with WebGL from a worker thread. So thank you very much for your time. If you go check out, I just tweeted links out to my Josh VR demo. Please build something, show me what you can do, tweet it to me, and then tomorrow come and visit our booth. And we have a couple T-shirts, actually. If anyone builds one today or tomorrow, come visit our booth, and we have a few T-shirts for any instances that people design that are really nice. So thank you very much. I appreciate it.